Mechanics courses series, which is the fundamental concept of geomechanics. This course is intended for graduated students, beginners, and junior geoscientist engineers. So we will make a brief introduction to how making a mechanical earth model. It is that to mention that we will not go through a lot of details. Since you have make my presentation, so no need to make this presentation. We pass there directly to the first slide. So after completing these courses, you will be able to define a mechanical earth model and state the contributing components. You will be able to state the sources of data used in mechanical earth model. You will describe the purpose and application of mechanical earth model. And finally, you can describe the sequences of steps involved with producing a mechanical earth model. This course contains an introduction. We have also a source of data, borehole measurements, and the mechanical earth model workflow. The mechanical earth model provides the context for introducing sources of geomechanics data that are involved with the modeling process. So the mechanical earth model is a concise record of all geomechanical information required to implement geomechanical workflows. It is not a reservoir model. We have to put this in our mind. It is not static geological static model. Rather, also it spans the entire stratigraphic section from the surface to all below the reservoir of interest. Before start talking about how to generate this mechanical earth model, we should know that in physics, model is just a model. It doesn't reflect the entire reality. So in physics, all models are wrong, and some of them are less wrong than others. That's all. You have to put in your mind that a model is a model. It cannot reflect the entire reality in subsurface. That's all. So the mechanical earth model comprises the best current information about our geological structure, mean the tectonic sets of nowadays and paleo structures, rock deformation mechanisms, also the rock mechanical properties, and the state of stress. When we talk about the state of stress, means we have a lot of state of stress including in our set. We can talk about the paleo stress, we can talk about our present day stress, and also the far field stress. The three components we have to make it in our mind to better talk about stress later in our comparison between the three sets of stress. The mechanical earth model is defined by a series of components shown schematically, including the mechanical workflow or the framework model, the mechanical stratigraphy, the mechanical properties, which are the Young modulus and Poisson's ratio. We have also the unconfined strength, UCS, and the friction angle. The earth stresses, pore pressure, the principal stresses, which are the vertical stresses, maximum and minimum horizontal stress, and the stress orientation. Which source of data are used to build the mechanical earth model? The data sources are presented in the order that information evolves in a new prospect. So we have by order, we have geological data, seismic data, we have also the drilling data, which is very important to calibrate our model later, and also borehole measurement and rock samples if available. If we have no rock samples, we cannot stop don't making our mechanical earth model. We can make the model, and after that, we can calibrate it with some empirical relationship if available. The first data used in our mechanical earth model workflow is geological data. These data generally are information that can be found in scientific journals and in company report. Also, we can use some offset well data if there is some data available in our adjacent areas or our basin information data there. So the tectonic history can be used to make the framework model, and also it can be used to make the principal stresses and stress direction. If our tectonic history is same, the tectonic is, for example, if we are in north of Saharan platform in North Maghreb for Algeria, for example, we have the active seismicity there. So the stress direction is the same as a fault. If we are in inactive area, the same, the stress is not, the paleo stress is different than present day stress. So we have to take this into consideration when we are building our mechanical earth model. The 3D geological model also can be used to make mechanical stratigraphy and also for the framework model. The earthquake fault plan solution can be used only if the region is active to make the stress direction and principal stresses. The word stress map, which is a very consistent database that I give you maybe the link later to download, or the latest one here. It can be used to make all the stress direction database that are in this website. The basin modeling and core description, all this geological information could be used to make mechanical stratigraphy and mechanical properties. For basin modeling for pore pressure, we have to be careful here because the basin model give a regional pore pressure. This value should be calibrated with in situ measurement. I have to take this into consideration. The second one is seismic data. The seismic data used in mechanical earth model are also 2D, 3D seismic data and velocity model. For the 2D seismic data, 3D seismic data could be used to build the framework model. Formation tops could help also in calibrating the mechanical stratigraphy. The structural interpretation is used to calibrate the stress direction for paleo stress, of course, and mechanical stratigraphy. This tool could help in comparison between paleo stress and present day stress. We will talk about this later. For the AVIO analysis, the output of this quantitative and seismic interpretation is, of course, 3D seismic cubes of VP, VS, and also ROBI, which are inputs for principal stresses, pore pressure, and stress direction. The check shot are familiar. All people are familiar with the VSP check shot that can give us the velocities that are used to make pore pressure and principal stresses. Here is the point. The seismic data provide the structural and rock property information over the entire volume of interest. And also, the seismic data can provide good comparison between paleo stress and present day stress state. How? For example, so we suppose that we have an in situ measurements in one well. We have calculated our present day stress. And of course, if we have available seismic interpretation data there, so all the fault interpretation orientation will inform us about our paleo stress. If the paleo orientation and present day stress of fractures or induced fracture are the same, so we can say that our paleo stress and present day stress are the same. So we have not very significant changes in our stress in this field. The seismic data are important for 4 reasons. The seismic data often provide the only elastic property data in the uppermost kilometer of depth, so in the entire section. Also, the seismic data reveal the spatial distribution of rock elastic properties and also provide only measurement below the reservoir level. The drilling data used in our mechanical earth model are from exploration wells, provide the earliest quantitative information about the subsurface rock formation. Here also, we should note that daily drilling report is used to calibrate pore pressure from where? From midweight. The drilling data are essential in the stress calibration. For example, we have to notice that leak of test, formation integrity test, and also extended leak of test is used to calibrate minimum horizontal stress. Borehole measurement are essential steps for mechanical earth model. This data is used especially from well logs and coring. The borehole images such as the FMI and UBI are used in mechanical properties, mechanical stratigraphy, and framework model. The sonic logs are also used in mechanical properties, pore pressure, and also principal stresses. The stress measurement, like we have talked about leak of test, microfrac test, are then used to calibrate the minimum horizontal stress profile. The logging while drilling and the wireline measurements provide high resolution geophysical data from the near surface to the base of the reservoir. some of source data borehole measurement are the rock sample. We have drilling, cutting, and cabins. We can use the rotary coring, and also, if available, some sidewall cores. Now we will talk about the mechanical earth model workflow. The mechanical earth model workflow is represented as a series of 10 independent steps. This figure shows the recommended sequence for building an internally consistent mechanical earth model. There are 3 levels of complexity associated with constructing mechanical earth model, with level 1 models being the least complex and level 3 the most complex one. The level 1 project in general have all the information required to construct and calibrate mechanical earth model available in one single way. Level 2 projects in general, for example, we have some missing data, for example, shear wave or density logs, or in case we have considered missing data from offset wells, or to model data using geological information. So we have to calibrate our data and using some empirical relationships there. The level 3 projects are intense high pressure projects. The projects are generally commercial one, and the outcome is a drilling program, for example, depends on the accuracy of the geomechanical data. It is very critical level of project here. Before starting talking about data audit, we have to know that it is important that all the following steps that you will see here are based on level 1 model for an isotropic elastic earth where the vertical stress is the principal stress. The data audit, which is a QC step, it is critical project planning tool. This step involves collecting the geological, seismic, drilling data, borehole measurements, and rock sample information. So in addition to collecting the data, the audit establishes which information is available for constructing a geomechanical model. For example, you can get your shear wave or compressional logs or density logs, but when you start to QC your data, you see that all these logs doesn't appear in your area of interest, in reservoir, for example. This is missing data that you have to notice and try to deal with this data at the real time before starting making your process. Now we will gonna talk about the framework model. Imagine in the figure, this figure, for example, that framework, this is a building framework. This is the output for framework. This is the result. This framework is a model depicted in schematic derived from interpretation of 3D seismic data. This model, what it shows us? This model show that the region was once in extensional tectonic set. See here, this is a fault, normal fault. So here we have the extensional tectonic set. So it is represented by a normal fault. But this fault nowadays is inactive. Why? Because we have unconformity. This unconformity will make stop to all things below for tectonics, sedimentation, and all things. So here we have separation between two sets, between two tectonic sets, and also between two stress sets. If, for example, the rock were brittle in the time at the unconformity, so for example, it is expected that natural fracture intensity will increase approaching this fault and getting high natural fracture here in this fault if this fault is brittle. Below this unconformity, the present day stress may correspond to the final stage of an extensional regime. But above this unconformity, we have uniaxial strain. This uniaxial strain condition may apply. So if the present day direction of minimum horizontal stress is in the fault deep direction, then the present day stress and the paleo stress might be similar. If the interval of sedimentation was long, so judgings of sediment above and below, here above and below, might be not similar. So this observation anticipates the possibility that elastic and the strength properties could be different across this boundary. The foregoing line of reasoning helps you to produce an internally consistent mechanical earth model. Why we are talking about this unconformity separation between the two sets of tectonic? Because we have to put in our mind that the unconformity separate two different tectonic and stress states mean we will not have the same stress strength response. It is separated, not the same tectonic and structural behavior. So the elastic behavior and here and here is not the same. The framework model captures information about the present day stress regime and the geological history of location, means paleo-stress. This model provides guidance as to what to look for data when constructing our mechanical earth model. Like we have talking about, before making the mechanical earth model, we should know if the region is tectonically active or inactive. For example, I will give you an example for Algeria. If you are working in the northern part, you have to take into consideration that you are working in active seismic area. So all hydraulic fracturing, pore pressure injection, production, all these things should be taken into consideration because you will perturbate your initial stress state. But if you are working in Saharan platform, in all basins of a Saharan platform, for example, Birkin Basin, Elysee Basin, you can bypass this this issue because you are not in a real active seismic area. Even we can make some little potential of reactivation faults, but it is not same as in the active seismic area. We have to know also, are the rocks poorly consolidated or well lithified? Also, we have to know, are there is any major unconformities, for example, for this one, or there is no unconformity, so we have continuity of tectonic set? Are there any fault or fracture zone in the area? The third one is mechanical stratigraphy. So the construction of mechanical stratigraphy from geophysical logs is illustrated in this figure. First of all, we have the geophysical logs, which are gamma ray, neutron, resistivity, and Berg density. These logs are then processed to get a coherent processed logs. After that, the core data are used to calibrate those logs. The information about the lithostratigraphy is used to build the mechanical stratigraphy, this one. The mechanical stratigraphy classifies, as you see here, strata according to the nature of the continuous load-bearing solid phase, either grain-supported or clay-supported facies. We have to know that these steps of mechanical stratigraphy is like you cover something. You cover the mechanical with the stratigraphy. You attribute each mechanical characteristic to its stratigraphy section. The fourth one is the elastic properties, which is very important to notice for inelastic and elastic approach. The both use the elastic properties. So the elastic properties profiles, for example, Young modulus and Poisson's ratio, are calculated using sonic and density log data. It is one of the approaches. It is not the only one. We have talked before that also seismic cubes can provide us from information, check shot. There is a lot of way, but the conventional way is using geophysical logs. So this figure illustrates the process of constructing these profiles. Sonic logs are processed to generate depth profiles of compressional VP and VS wave velocities. These are edited and depth shifted to the density log so that they can be used to compute dynamic elastic parameters using rock mechanical properties equation. Very important remark is that the elastic properties getting from the geophysical logs are dynamic models, so we have to calibrate them with either possibility from calibration from empirical relationship, or we can use conversion of locally relationships. The actual data rarely show such pronounced steps. Why? Because the rock composition and texture often are more gradational, not than this one. This is typical one, and for in the who works in a static model knows that in the reality we have a lot of gradational. So a lot of times we bypass these steps. We go through directly from bulk density to our static model used to use it after later in stress profiles. But preserving this step-like profile is a reminder that the mechanical earth model is just a model. So the step-like character of these subsequent profiles reflect the influence that mechanical stratigraphy has on the model in elastic properties. This is why we have shown these steps. So the rock strength now it is five step. The profile of rock strength parameters are derived from data used to construct the mechanical stratigraphy and also from elastic property profiles. The undefined comprehensive strength UCS can be estimated from lithology and porosity data or from static Young modulus. Static one, not the dynamic one, means the converted one. If the lithology porosity approach is used, separate model from grain support and grain support facies apply. The friction angle is computed from V grain obtained from the volumetric analysis defined from the mechanical stratigraphy in the previous step. UCS and friction angle are calibrated to laboratory triaxial strength measurement made on course. And this is very important steps. If we have core, we have triaxial data, it is better to calibrate our UCS unless it is not consistent data. The overburden stress is calculated by integrating bulk density over depth. Generally, we have not all the density to the depth, to the top of surface. This is requires density log run to the surface or formation density, estimate between the top of the log interval and the surface, which is not generally the case. Exploration wells typically run density and sonic logs to the surface, but for development wells and production one, we have not this opportunity, so we have to use some relationship to get density until the surface. So if the density logs to the surface not available, density profile is constructed using density and or sonic logs from offset wells over the stratigraphic section of interest, or Gardner method is commonly used to model density profiles from compressional wave velocity from the DTC. This is the steps. In general, there is no direct calibration for vertical stress. This is very big issue for geomechanical engineers, but occasionally the hydraulic fracturing stress measurements measure the vertical stress, but this is a very rare exception. It happens when the induced fracture propagate in the horizontal plane of fracture. The primary opportunity to improve the overburden stress model is to measure bulk density over sections where it had been modeled, if it is possible. If it is not possible, no need. Now, pore pressure, which is very crucial input in mechanical earth workflow. The pore pressure profile is modeled through shale section using Pore or Eton methods. Both methods can take compressional wave VP, deep resistivity, gamma ray, and sonic as input data. The pressure in adjacent permeable formation is assumed to be in equilibrium with shale, except when the centered effect must be taken into account. The pressure in shales is represented by dotted line. Here, we have to be careful because when you are modeling the pore pressure within sandstone reservoir, it is totally different when you model pore pressure within the shale reservoir or unconventional reservoir, because as you know, the unconventional reservoir are very overpressured reservoir. So you have to take carefully the information given from the logs, we have to calibrate our pore pressure profile with some, if we have the mid weight or pressure from well testing or formation pressure data, because the pore pressure in shale reservoir, it is very overpressure zone. We have some layered, you can pass through overpressure layer and gone to hydrostatic one and vice versa. So the pore pressure is very crucial one. I know that until nowadays we cannot get a real pore pressure calculation, but we can calibrate our data with mid weight or like I have said, formation pressure to avoid misunderstanding of pore pressure. Because uncalibrated pore pressure profile often shows general trends of pore pressure via depth, but the magnitude of pore pressure can be seriously in error. You can imagine if you have pore pressure value in error and you are dealing with a very overpressured reservoir, it will give you very damage. You have an example of deep water reservoir, which is a very big issue of geomechanics. We have, yes, I know that cement and also the pore pressure was not very good estimated there. Eighth one is the minimum horizontal stress model. So a lithogeology dependent profile of the minimum horizontal stress can be constructed using one of the following approach: inelastic model or poroelastic model. For me, I use the second one, which is widely used because it builds upon the mechanical earth model steps 3 through 7. It used to model the minimum horizontal stress profile as well. So from bulk density and sonic logs, we built a VP and VS and Rho profiles. Those are used to contract dynamic elastic moduli profiles, Young modulus and the Poisson's ratio, which will be calibrated with core data here to build the static Young and the Poisson's ratio moduli. The SH means minimum horizontal stress profile can be calibrated using laboratory data, or we have to use in situ measurements. Laboratory tests are used to measure the K0, which is the stress at rest, and the static elastic moduli. The in situ measurements of pore pressure combined with laboratory calibration will improve the prediction of minimum horizontal stress. You have to know that if you don't calibrate your minimum horizontal stress, until this, it's called estimation. If you have not direct measurement, which are Likov test, microfrac test, or hydraulic fracturing data available, all this model are just estimation or prediction. It is not direct physical information. So the most accurate profile of minimum horizontal stress are calibrated to these direct measurements. Or if you have drilling data like Likov test, you can use it later to calibrate your model. For maximum horizontal stress, it is here we have an issue, because for minimum horizontal stress, like I have said, the in situ measurements, frac test, and the microfrac test or Likov test can calibrate our model. However, for the maximum horizontal stress, there is no direct measurement. There is some theory invented by Anderson faulting theory or Barzobak to make, yes, to know that we have the same steps used in minimum horizontal stress are used to build the maximum horizontal stress. The difference is that the calibration. So the researchers invited some relationships to calibrate, or there is an alternative method, which is construct a depth trend for maximum horizontal stress based on least squares and feed this value of maximum horizontal stress obtained by modeling wellbore damage. This approach is often used early in the life of a field when data are sparse. And there is also another approach, which we call it the upper limit of maximum horizontal stress. This is developed by Zobak. Also, you can use this method to calibrate your data, but you have to be careful that most of maximum horizontal stress data in the world are not calibrated. But if you calibrate if you have calibrated vertical stress, minimum horizontal stress, calibrated one, and pore pressure taken into consideration mid-weight and pressure data, you can go through your model. Well, I have told you before starting this presentation, it is just a model, but be careful when calibrating your model. The final steps, I don't know if we can call it final or the first one or middle one, because stress orientation profile can be generated at any time since it doesn't use any input from other mechanical earth model profile. The stress orientation don't use elastic or logs or stratigraphic framework. So the stress orientation is obtained from interpretation of well-bored image measured either by multi-arm caliper or on the orientation device, or also the widely used one nowadays is the borehole images, for example, the FMI or UBI from Schlumberger that are widely used nowadays to infer our azimuth of induced fracture or breakouts. The breakouts give us the azimuth of minimum horizontal stress because it is the well elongation, and azimuth of maximum horizontal stress is inferred from induced fracture. This is due to the orientation of our stresses. It is related to hydraulic fracture. The caliper method provides an estimation of minimum horizontal stress and borehole images of elongation. Borehole image is more accurate since the orientation of minimum and maximum horizontal stress are determined from well-bore breakouts and drilling induced fracture. The caliber-based interpretation methods are also designed to differentiate stress from induced stress elongation from other sources of well-bored image, because we have a lot of sources of well-bored damage. We have not only the stress induced. Be careful when interpreting your caliper-based data. However, it is also recommended that the interpretation be checked using borehole images, FMI or UBI, when possible. So also we have to notice that there is no calibration steps for image analysis, as this is the most direct method for determining stress direction. I will give you just, I will come back here. Sorry. We have talked about earthquake fault plan solution, which is also method to infer the stress direction, or like I have told you, if you are in active area, for example, in Algerian northern part, there is a lot of earthquakes, so you can get your focal solution, but those one can give you the orientation of stress direction, which is direct measurements. The world map stress also, it is a database that give you information about your stress orientation. If you are in an area without a lot of changes and you want to gain time, you can use this information and bypass all this calibration. I think that by making these steps, we are in our final steps. So we have to mention that it is highly recommended that geomechanical models be revised as critical missing data or calibration data become available. Model revision can entail acquiring new data or simply improving calibration. The calibration of pore pressure, earth stress, magnitude, and a better understanding of lateral variation in rocks' mechanical properties are typical example of model refinement. Here we have the tree of mechanical earth model revision. We start by data editing, we build in our mechanical earth model. If we have new data, make the revision. If forecast agree, field data also can be included in our input. And this is the tree. I can now say thank you. Shukran lakum for everyone. Merci pour votre attention. متشكركم and see you in the next courses if you are interested in petroleum geomechanics courses series, which will be a lot of courses in this series. Thank you very much.
Thank you, Mr. Youssef, for this interesting presentation. I think that all the participants benefit a lot of information from this presentation. So thank you again for your time and effort. Also, I would like, we have some questions into the Zoom chat.
Okay.
We have a question from Khalda. Khalda is saying, can you explain how to calibrate overburden stress?
This is very big question. Overburden stress, like I have mentioned, we cannot calibrate overburden stress directly. However, if let me come back this slide. I will give you the explanation because if the hydraulic fracturing involved get in the horizontal plane, so now it will be like, for example, how we can calibrate our minimum horizontal stress. It is by getting the information from hydraulic propagation of hydraulic fracturing. This is the microfrac test or hydraulic fracturing test. So this propagation data I will explain. Imagine that you are in a well bore and you isolate your section. You are in a horizontal plane. So you start making your hydraulic fracturing in a normal way, in a vertical way. The fracture will propagate in the vertical in the vertical way. So in the first point, your closer pressure here, it is related to horizontal stress. But for example, you are in a horizontal well, or the fracture propagate in the horizontal plane. It will not go in the vertical plane. Here, it is like your horizontal stress will become the vertical stress. So you will calibrate your vertical stress by the closer pressure. I don't know if you get the information.
Okay, thank you. I have another question. Can you please give more details about how we can use seismic data in geomechanics study?
Yes. Okay. So the seismic, you have to know this. This is best picture that can explain. Here we have for example, the well. Here we have the model. Imagine that this is Earth and this is only one point. This is in situ. This course will be, I will give the 3D seismic geomechanical courses later, but I will give you a brief explanation. This one, all what we have talking about is it from well. These data are, you have to imagine that your wells give you geophysical logs. It means in one point. But the seismic data is like a comparison between vector and matrix. So the well is just vector, and the seismic data is a big matrix. So the same data that is issued from the well means the VP, VS, and rho V, compressional, shear, velocity, and density logs can be inferred from seismic by using the seismic inversion. So when you make your seismic inversion, means the AVO analysis or quantitative interpretation, you will get a rho V, VP, and VS seismic cube. Means all the equation used to build 1D geomechanical model are also used to build the 3D geomechanical model. The only difference is the huge data. The same approach, same techniques, same steps. Did you get the information?
Okay, thank you, sir. Another question. Can soil boring data can be used for overburden calibration in shale sections?
Can soil boring data can be used for sections? I think that we cannot because we have to be careful about overburden calibration. Overburden calibration in a lot of exploration wells, you can get the data. because in exploration wells, we are very interested to acquire data from the top to the reservoir. But if you are, for example, in development or production wells, you have not this data, so the calibration is not very good. So there is an approach that I didn't forget to tell you. We call it the gradient. We can use hydrostatic vertical gradient or lithostatic gradient. If there is no big changes in your tectonic sets, present day tectonic sets, you can use 1 psi per foot lithostatic gradient to calibrate your vertical overburden stress. It is in generally the case. And also for pore pressure, if the area is known, there is a lot of wells and it is known by the inactive tectonic sets, we can use pore pressure gradient for 0.43 or 0.45 psi per foot. But be careful, I don't tell you that vertical the stress and the pore pressure gradient are these values. Be careful. This is if you know very well your region. Thank you.
Okay, thank you. We have the last question.
Okay.
How to calculate pore pressure for formations with no compaction trend?
We have the D exponent approach, but this is very detailed explanation that will be explained in geomechanics courses later also. So you have D exponent, we call this approach D exponent. If you have no NCT, it is non-trend from shale.
Okay. So thank you, Sir, for this.
I think that we have a question here. Which study is better for oil exploration product, geomechanics or static modeling? Oh no. I have mentioned before that this is not static model. I will think that this is the last question I will answer and we will close the session. So which study is better for oil exploration projects, geomechanics or static model? Both are essential. We cannot bypass one and one. For geomechanics, it is used from exploration to appraisal phase. We use geomechanics in exploration phase, in development phase, production phase, all phases, and also in the abundant phase. The static model also, it is very important in the last exploration phase and the beginning of development phases. So we have to combine geomechanic and static models. So the output of static model could be used in geomechanical model, but the output of geomechanical model are not used in static model. But both are important exploration projects. It depends on the degree and in which level you are. Thank you.
Okay, thank you, Sir. So I think that it will be the end for our session today. So thank you all for all the attendees for their time attending the session. Also, the great thanks is for you, Mr. Youssef, for this interesting session. A lot of information will or were handled to the participants. They benefited a lot of information that can benefit them in their current and future career, inshallah. So thank you.
Thank you all the attenders, and see you soon in the next courses in this platform or in other platforms. See you soon. Thank you very much. And feel free to contact me with this. I will share my emails. You can contact me here in emails for further information, or if you require any additional informations or some program schedules or of the upcoming courses. This is my email and this is my WhatsApp contact. Thank you very much. See you soon, inshallah. Shukran lakum. Merci pour votre attention.
Okay, thank you, Mr. Youssef. So I would like to remind the attendees that if they would like to have certificate for attendance, you can fill into the form that was sent into the Zoom chat. Also, I would like to remind you by the enrolling into the 2 upcoming workshops, 3D modeling for natural fraction reservoirs and also the integrated production model. So thank you again, and we have 5 minutes. You can fill into the form that was sent into the Zoom chat. Thank you again, and hope you good night, inshallah.
Inshallah. Thank you.
Salam.